All righty, welcome back, everybody. Hopefully everything's getting along well for you. Not going too lost in the class so far. Any questions over things? Everything going good? Kind of review. Let's kind of go back and think. Our last class, like I said, we're really ahead right now, but I'm kind of building in a buffer. Mainly because I really want you to have time to think about chapter 3. Mainly vocabulary, because as you've kind of seen, your calculator does a lot of the work for you. Okay, it's gonna keep continuing in that vein, which is a good thing. Some slight times you're gonna have to do some simple calculations. In the last class, we talked about measures of center, okay, which we saw with mean, median, and mode. You saw the formula for measures for mean, okay? And with that, you know that you can use your list function on your calculator, which always helps. Okay, we're gonna be using that again today. So if you're good with the calculator, hopefully you've gotten your calculator. If not, like I said, you can still get by with that scientific right now, but there's gonna come a tipping point really quick, okay? So make sure you got that calculator. One student, and probably in this one, so I'm not throwing it around. I guess if you got it from the high school, it may need to be charged or new batteries, but I don't have a way to charge it. I'm looking into that, okay? So if for some reason yours needs to be charged, like I said, I'm looking into it. I have a charger in my office, but it hasn't been working too well. But if I can get that thing worked on or fixed or even buy a new one, then if I need to charge it for you, I can. Okay, other than that, you have to take it up with the school. And for us, you have to take it up with the, if you got it from us, you have to get with the tutoring center. Okay. So remember with mean, what is something that affects a mean?
An outlier.
An outlier. That's why you get those skewed points, you know, the skews. I say that because it's going to be a midterm question, okay? But you'll see those little troughs. So look for the troughs, okay? And that's always going to be the side that's going to be skewed. What's always going to be your highest point? Mode, then median, and then depending on which way it's skewed, right? It's kind of nice because if you know your median is always going to be the middle guy, okay? So we're kind of good with that. Now we have learned some Greek. If you see Greek, what are you seeing?
Population.
Population. Greek in this class is always going to denote population, okay? What would be a symbol that we would see for samples? X bar, like a sample mean. Now, what would little n be? Sample size. Big N would be population. Very good. These little things are just going to kind of help you moving forward because we're going to keep seeing this stuff a lot. So when it happens, you go, oh, big N, that's all that means. What would be the symbol for population mean?
The mu.
The mu. Remember, it looks kind of like a backwards Y kind of thing, not moo. Remember, like I said, not cow. But mu, it's got like an MYU kind of sound. I always put MU, and that's how it's spelled. But it is mu. It's got that little bit of a Y kind of in it. So today we're going to get into dispersion. Okay. Dispersion says this. You know what the center is now. You learn what the calculations for center is. Later on, I have a really cool kind of video I'll show you about measures of center because it'll flow better into that lesson. But as we start to collect data, whatever it is, I don't care what it is you're deciding to collect, things tend to gather up, okay, toward the center, okay? And so we have those measures of center, the mean, the median, the mode. But if I gave you a big tub of clear, perfect water and it's completely clean, and then I take like a really just high concentrated dye, okay, and I just dump it in directly in the center of it, what's going to happen to the dye? It's going to do what? It's going to start to disperse out, right, and get lighter and lighter and lighter. But where at least in the very beginning, in the center there, it's going to be really dark because everything kind of gathered there and then moved out. And that's what we're going to learn today is basically the move out part, okay? How things start to disperse from the center, okay? Because that matters. Why? Well, look at some of the things I have here. If you're gonna go to the doctor's office and you have an average wait time for the doctor's office, and like I said, stay here 30 minutes. So you call up, you say, hey, I'm not feeling too good, but I don't be waiting all day long. How long is the wait? And they go, it's about an average of 30 minutes. Does that sound pretty good? But it's average. So that means you could walk in literally, okay? Think about it. Could you walk in and wait 2 minutes? Could you walk in, give them your name, pay your copay or whatever, and they go, hey, the doctor will see you now. Good, couldn't you? But you could also be waiting an hour. Remember, it's average. So you could be waiting from here, or you could be waiting from here. It's an average time, okay? Notice that's a dispersion of time from the mean that they gave you, okay? What's the problem with this one? Average rating of a certain thing off Amazon. What's the problem with that?
It's qualitative.
The trick. Why would you pay taking an average? Because remember we talked about that? Because since it's qualitative, we don't use averages because averages are really affected by what?
Outliers.
Outliers, exactly, very good. Now, does that mean it's bad? No, I mean, let's face it, like, am I gonna kind of mentally average stuff in my head a little bit? You know, when like looking at things, yeah, I get it. So if you said the average rating of this thing, off all what I'm gonna buy off Amazon, whatever, there it is. But it's not something I'm gonna start advertising, which you will see, okay? How many times you watch those like dentist commercials that says 1 out of 5 dentists or 4 out of 5 dentists saying this average choose makes them happy. Well, that happiness, you know, that's kind of like that. Average temperature of Juneau, Alaska in October. Well, I've been to Juneau, Alaska a lot in October. And the temperature now, average temperature, if you call Juneau, Alaska, they go, oh, our average temperature in October is about 30 degrees. That's cold, right? That means whenever I went to Juneau, Alaska one time, it was 80 degrees. I dressed a little too warm, or, you know, for that kind of weather. And I showed up one time, it was negative 55. Okay, so notice, average doesn't tell you a lot as much as dispersion. Okay, are you kind of with me so far? Okay, so we're gonna learn about 3 different types of dispersion today. Okay, and I'm really gonna hit in slowly and really hard on really standard deviation. If you go back to the first day of class, I said to you, man, I get it. Eventually, I'm gonna run into you in the real world, out in the wild where you roam free. And I hope that some of the things you learned in this class, you're still kind of using, okay? I'm a broken record when I say this, but like I said the other day to a class, I said, I've still never used the quadratic formula, and I promise you every day I'm looking. I'm out there, you know, going, is today gonna be the day? But there's not a day that in some way, shape, or form, I don't use statistics, maybe not in the literal sense, but I'm a big news watcher. I watch the news in the morning, they say some things. And because of what I've learned in this class and now teach, my antenna kind of pop up every once in a while. When they say something, I'm like, well, wait a minute, that didn't sound right. And maybe it was right, but at least my antenna are firing. It's making me want to think a little bit deeper about some of the things I'm hearing, okay? And one of the things you're going to hear a lot, you're going to hear standard deviation a lot. You'll hear the word variance a lot, but I hate to say this, I think a lot of people that use the word variance don't use it correctly. Okay, well, we'll get into that. So the first thing we're going to learn today is going to be range. Here is your definition of it. Range is the measure of dispersion. That is the difference between the largest and the smallest values in the data set. You've done this before. You've seen range before. I know that because whenever I taught 7th grade, I taught range. Okay, that's as far as we got. We got range. So this is the sample amount of minutes observed for 2 cell phone users talking. Okay, let's be honest, people don't talk on their cell phones anymore. Could just put texting. I guess that would never stop. Notice the data is not in order. You don't really have to put it in order. Unfortunately, this is one of those things your calculator doesn't do for you. But it's simple math. Okay, super simple math. It's not gonna be like somebody like now trying to find the integral of some sort of like, logarithmic equation, okay, function. So notice here, all you're gonna do is you find the largest piece of data that you have there and the smallest piece of data, and you're gonna subtract it. I'm gonna come in here, I think I've already got it, yeah. Take your largest that you have very simply there to see. Okay, and so you can see that the range here, okay, range is equal to, we're gonna have this 44 minus 2, which is obviously equal to 42 minutes. What is that telling us though? Now, I don't have a mean right now. Range is really good when you already have a mean to work with, which you could obviously find very simply. Put in your list, hit calculate, right? Now, look at what you could say with the doctor's office example. If you actually had a sample of some of the data of actual waiting times, right? And this nurse who's looking at her computer screen whenever somebody calls and says, hey, how long is the waiting time? If the computer was doing it correctly, she could say, hey, our average waiting time is this, right? That would be the mean. But couldn't you, from that mean, knowing range, you could easily go cut that guy in half. 21 minutes this way, 21 minutes this way. There's a range in there, right? Notice, so it can disperse. So she could say, you could be like, if you're non-mathy, you can go, well, how long is it? I get it, it's an average, but how long do you really think I'm gonna wait? And she could say, hey, look, you're gonna wait probably be here, look, you wait 2 minutes, you can wait up to 44 minutes. That's what a range tells us. It gives us a possible amount. Is it perfect? No, nothing's perfect now. You're in statistics, okay? Everything's kind of fuzzy at times. The more data we get, the more the numbers are gonna change, okay? Good with that so far? Range, super simple, don't really need to hang out on too much, right? I mean, you get a question on Hawk saying, what's the range? There's no calculator button for it, okay? You're just gonna have to go in there and just go, okay, well, do my minusing and be done with it, okay? But here we go. Next one we're gonna look at variance, okay? I'm gonna hang out a little bit on variance, and then we're gonna jump into standard deviation, because you have 2 tests coming up after we get done with this chapter. We got 3 to go through, and then I want to make sure we hit in some review over 1 through 3, mainly 3, because then you have your chapter 1-3 online test that you do online at home. Just so you know, you've all taken math here before, but it's well worth reminding you. You only have so many chances to take the online test, okay? If you don't pass those 2 chances, that does not mean you're done. All you simply have to do is email me and go, hey, I used up my chances. I don't need you to tell me why. I don't need an excuse. I don't need, just tell me I used up my chances, and guess what? I'm gonna go right in there and give you another chance. That's it. It's simple as that. So don't stress it out, okay? But I wouldn't wait either. Like, don't wait till like the night of when it's gonna be due at midnight, because I'm probably not gonna answer you till the next day. Okay, because my phone goes on do not disturb about 10 o'clock. Okay. So just kind of be warned about that. But I don't mind. Now I do have a rule. I don't open it up but once every 24 hours though. Okay, because I'm not gonna be sitting there like you sitting there guessing and like going, oh, I hope. No, you need to go in there and study what you missed, okay? Because it will allow you to study what you missed. Added on to this though, okay, and this is an in-class test you'll use on these computers or in the computers over online. We'll be using Respondus Lockdown Browser. It's your chapter, it's your empirical rule and percentile quiz. It basically is this right here. Can you understand these things? Okay, from chapter 3, okay? Super simple, okay? Not real mathy, but it does have a lot of, you're gonna have to remember how to get to things on your calculator, okay? There's not a whole lot of math involved, but you're gonna have to know how to get stuff. So after having said that, let's get into variance. Once again, two kind of ugly formulas. Okay, they always look horrible until you realize, oh, wait a minute, I'm in stats now. My calculator probably gonna do this for me. That's the nice thing about the uglier I'm lying to you. There is one formula out there I'm about to show you that your calculator doesn't do later on. But we have a chart that we use, okay? Let's dissect this real quick because I really don't want you to get lost, okay? Everything's always fine and dandy until chapter 6, and then things get a little abstract and people just, they forget everything. It's like, let's not do that. What is this guy right here? Yeah, population size. So we're just gonna put pop size. This guy right here.
Sample size.
Sample size. Okay. What is this guy?
U.
Which is
Population mean.
U. Population mean. Always read this one as X bar. Okay. What is this one?
Sample mean.
I'll give you this one. Anytime you see just an X with an I, that's just the data, a piece of data, okay? So here I've got some data. What are we calling him?
Summation.
Summation, right? You wanna know why? Watch this. Summation. We know he's summation. His actual real name is what? Capital Sigma. Guess who else is Sigma? That guy right there. He is also called Sigma. Okay? And we will be calling Sigma. Okay? So he is going to be the Sigma that we use from this day on. So when you hear me say the word Sigma squared, I'm talking Greek, which means automatically your brain should automatically say what? He's talking population, exactly. I'm talking population. So that can narrow things down. You go, okay, he's talking population. What does he mean by squared? Variance. He's talking variance right now. Okay, good with that? Okay. So notice sigma squared is population variance. Okay. S squared, it's a variable. It is in Greek. Okay. That's going to be sample variance. Okay. Are we good so far? I don't want, like I said, I don't want you to get too hung up on stuff, which is why I kind of keep repeating it. But there is something different. Remember when I showed you mean? It literally showed you the same equation twice, really. I mean, if you really kind of, let's be honest. It was the exact same equation twice, except population had a big N, sample, little n, right? What's the difference about this one?
Sample size -1.
Why is there a -1? I want you to stretch your brain. Why did we have a -1? Why didn't I put a -1 earlier in the mean? But I am right now. And you can't be wrong if I'm telling you to guess. Put it that way. So don't worry about like. It's kind of a weird thing to just see a -1 in something, right? I just thought I would be like, it's there for a reason. This is called correction. Okay. What this is saying is this. If I'm dealing, and remember this, when you're dealing with populations, there's an N there, right? I know the population. There it is. I have everything. I know all the numbers. If I'm studying a sample, is there a possibility I missed something? Like maybe I collected one more piece of data than I should have, and maybe there was a little bit of a extra accounting error. Does that kind of make sense? Like a little bit extra of something, because it is a sample. It's not perfect, right? Because remember, statistics isn't perfect. That -1 as in just a level of protection, a level of correction, in case there's maybe double data that got accounted for somehow. Okay, so it's that little kind of, we used to, in big stats, we call it continuity correction. It kind of helps things kind of level out. It does work mathematically, which is beyond the scope of this class, okay? But if you prove that n minus one to infinity, if you ever take calculus and take it to the limit, it works perfectly. And it actually, because if you don't, it shoots off to infinity and it doesn't work anymore. So it's kind of weird how that shows up mathematically, okay? So that n minus one, it's built in. Do you need to kind of remember it? No, it's good for your head knowledge right now. Okay, so when you see it, but remember, your calculator is going to do this. Okay, but I do want you to have that conceptual understanding right now that we need to have some sort of like levels of protection, because this is samples. Samples we're going to get into chapter 6 and beyond. Right now, everything we're going to do is in population mode. Okay, we know everything. Okay. Here I'm going to show you variance. Notice example. The number of rods Jesmond has given over a sample period, a sample of a 5-day period. So it's saying sample, right? Okay. I graphed this. You'll be doing this graph right here in chapter 12. This is called a line of regression. Okay. If you're big into the new AI craze, this is one of the ways the AI was trained, is using regression models that you'll learn in chapter 12. Okay. But notice, look at my formula over there. I have this x minus x bar. That's just the piece of data minus my mean, right? And then I square it. Because what's happening here, that squaring, okay, if you go back in time in math, that squaring gets rid of the negative because I'm looking at the distances. Kind of to that mean, that regression line, okay? So kind of help out just a little bit. Variance is hard to understand. I'm not even going to lie to you today. Variance is really weird. Okay, I'm going to show you why. If you look at this one, once you look at this, you've got x minus x bar, you square it. Okay, then to get your actual variance, if you were going to do this the long mathy way, for those of you who don't want to get your calculator, you're like, I'm going to do it. Good job. I use my calculator. You would have to add all those up after this. So you'd have to calculate each one of these separately. So I'd come in here and calculate this one, this one, this one, this one, and this one, and then add them up. Notice when you add them up, what are you going to get? It is super simple math. 10,000, uh-oh. So you're going to get 10. What would be the symbol I put in front of that? We're dealing with variance, right? Am I going to be using sigma squared? S squared. Why am I using S squared?
Sample.
Notice what it says, sample. That's going to be important later on. Knowing when you're using a population or a sample, you are going to get two different numbers. Because the sample, there's that continuity correction, that n minus one that your calculator is going to be it's going to be counted in that, okay? So be careful. So yes, this will be S squared, my sample variance. Well, what does that honestly mean? Okay. What this means, let me see here, do I have a, yeah, good. I want to make sure I didn't, sometimes I erase certain things. If you have a mean, and I'm gonna explain this as kind of a half truth, because why muddy the water, right? Let's kind of keep it just, if I knew, you know the mean of this guy, right? See, the mean is 4. I know my middle number. Do you see how that 10 is, it's kind of close to 4, but not really close to 4, right? The closer your variance number is to your mean, the less variability. Think about how things vary, okay? The less variability there is. Think of it like a pendulum, the swing. There's less swing, whereas this swing is kind of staying right there. This one's got kind of a little bit of a swing to it because it's kind of out there a little bit. That's about how I want you to understand variance. Like the larger the number is, the more it's swinging away from the mean. Okay, so think of like the first question we had when I showed you like the data. If we could find out the middle number of those the time people were in the call, the mean, we can see how much is the swing, okay? It's not the range. There's a difference between this and the range, okay? They are measured differently. This is just saying how much does something vary. They use it a lot in factories. Here's the irony. Okay, think about potato chip factory. While we all get bags of Lay's potato chips, we open it up like, how much air did they put in this thing? It is still weighed, okay? And it's allowed a certain amount of variance as it's coming up, because no potato chip weighs exactly the same, okay? Even though the bag will say, there's a pound of potatoes in there. It's never a pound. It's always gonna be allowed a little bit of a swing. And if something's outside too low or too high, it's gonna get knocked off the conveyor belt. That kind of make a little more sense what variance is. A little bit. It is still conceptually hard to understand because we don't think in variance. That's a squared number. What's the difference between that squared number and the rides? Are those rides squared? Are we measuring those rides in square units? No, she rode 3 rides, 2 rides, 5 rides, 6 rides. Those weren't 9, 4, 25, you know, that's not how that works. So notice variance kind of, it's a little bit harder for us to intuitively understand, okay? Which is why we don't use it a lot. Now, there's always 1 or 2. You future computer science majors or people who are getting into computers later on, we use variance a lot, okay? When I do coding at home, I like to use variance because it's real hard to program in anything else, and the computer really likes it, okay? So just kind of a heads up about that. Well, we've learned about range. We've learned about variance. You're about to learn about standard deviation now. Okay, so here's standard deviation. Standard deviation is going to be our go-to guy. Beyond mean, beyond probabilities, standard deviation. Okay, I would say the 4 major, like if I could say, hey, these are going to be the 4 cherries you're going to have in this class: mean, standard deviation, probabilities, hypothesis. Okay, that's it. But really, standard, if you can walk out of this class a year from now and still understand standard deviation, I kid you not, you have a leg up over 99% of the population. Automatically. That's even if you don't remember how to do the math, because you're not. You know why? You use calculators. You might as well get a calculator. Okay? But when someone says standard deviation to you, which they say a lot on the news, in articles, they say, oh, this thing was so many standard deviations away, or da-da-da. You can go, I know what that means. And then you'll know, that doesn't make any sense what they're telling me, or, oh, that's not so bad. Okay? So what is it? Well, look at it carefully before I even show you. Hey, let's go back in Matthew land. If I gave you something squared, how do we get rid of it? What's the inverse of a square? Square root. How would I get rid of sigma squared? There you go. It's just the square root. So if I gave you the variance of something, how would you, now I gave you the number. If I said this is the variance, how would you find the standard deviation? There you go. Ooh, so hard. Right, right? I mean, really, that's as hard. But what if I gave you standard deviation? How would you find the variance? Right. Yeah, that's just basic, simple inverses, right? There you go. That's it. You're noticing there, population, standard deviation. Once again, when dealing with population, what do we have here? Greek. Here, just a variable. Okay, notice we don't have any squares though. So when I say and will say, and will continually say, and chapters will say sigma, sigma, you know they're saying standard deviation. That's exactly what they're saying to you. And it's going to be said a lot. This symbol is here to stay. It's gonna be here. It's gonna be a major, major player moving forward. Okay, to understand things. And by the end of this lesson, you're gonna have a better understanding of what it is when it's all said and done, okay? Does it matter if I'm dealing with a population or a sigma or a S, a sample? Yes, you're gonna get different numbers now, for sure. Why?
And minus one, the correction.
Look for the correction. There's a correction and there's correction built in, so you're gonna get some slightly different numbers, okay? S we'll deal with later. Okay, you're gonna see it pop up every once in a while, but right now, we're gonna be dealing a lot with sigma. What's gonna happen later on in class is we're gonna be dealing with stuff and it's gonna be like chapter 7 or 8, or I forget which, it'll say, hey, this is how you figure this out. Sigma known. Hey, this is how you figure this out. Sigma unknown. It's literally saying, hey, if you got the standard deviation, do this. If they don't give you a standard deviation, do this. And that's how it's gonna work, okay? Are we good? I don't want to gloss this over. Is everybody good about seeing the Greek? I know I sound like I'm repeating that a lot, but just trust me. Are you getting what Greek is population? Variables are going to be, except for the n, okay, so I gotta leave that out. Except for the n, the name of stuff, but the variable is going to be samples. Okay. Look right here. I'd work this on your calculator. Try out, see, can you match that? Because you're not gonna remember how to do it if you can't match it. Okay? Let's click over here to my calculator and we'll do it together. This is what we're gonna end up with right here. I'll give you the data again, so just kind of follow along with me. We're gonna hit stat. Everybody see my screen okay, or do I need to go a little bit closer? Because I can go about down to here that way. I will say what to press, just so you know. Okay, so you're gonna hit stat. Okay, hit enter. I'm going to go up here. Let me hit clear on my stuff up else here. All right. First, 11, 18, 25, 51, 44, 29, 30, 17, 29, 7, 52, and then 60. Everybody get those in okay? Like I said, just, I'll wait up for you. If you need me to repeat anything, just tell me where to start repeating from. Everybody good with that? I'll click back down. Notice from here, okay? I'm just gonna go ahead and hit my stat again. You can just click straight into your stat button. You don't have to quit. You can just go straight into stat, hit stat. Click over to calculation, hit enter. Make sure, notice on mine, on that frequent list, I have something listed there because I was using it. I need to go in there and get rid of that because I'm only doing the calculations in one. It calculated. As I click back over to my screen, notice what I got there now, and I'll pull it up here. I'll look at it. Do you have a mean? What's your mean? Which is 34.41666. Okay, there you go. Look what I have highlighted. Doesn't that say sigma? Yeah. There you go. It just did your standard deviation for you. Okay, so your standard deviation here is going to be, now, hear me. It's gonna get annoying. Most of the time, you're always going to round sigma to the nearest tenth. Okay, so notice our sigma here is 15.2. Okay, the reason I'm using, why, does anybody see why why am I using sigma and not the S that's right above it? Yeah, look here, this guy right here. That's sample. But look right here, that says every. Okay, that's how, if you're getting red bars, that's probably what's happening. Is it's saying, are you dealing with a sample right now? Or are you dealing with a population? Okay, so you gotta read it carefully, okay?
Tell us what to round to, or is it just?
Always, there's a rule, and it says it in your book, it says it in your textbook, but Hawks is gonna, for sample standard deviation, it's going to say round to the nearest tenth. Usually for standard deviation, that's the rule, okay? If they want anything else, they will tell you, okay? So good on that, because that's, I promise you, that's gonna be one of the more annoying things in this class is not rounding to the right decimal point, okay? Good on that one? Remember, we're always gonna be using one variable stats. This is not a multivariate stats class, so you're always gonna use that guy. So far on your calculator, you've really learned how to do one thing, but you've got 3 things you can do right now, right? Can we name them? Well, actually, 4 things. Let's name it. We've got mean. What else? Median.
Sigma.
Just with a button, just with a button. You got sigma. What else you got? Sample, right? And that's buttons, right? Now, what if I ask for the variance?
You would
Square that.
Square that number. Let me give you a little hint. If it asks for the variance, it's still going to want you to round to the nearest tenth. You can't square 15.2. You're gonna get the wrong answer. Remember, whenever you're gonna have to round to something, you need to go to one data point beyond. So notice I would actually square the 15.21, square it, and then see what needs to be rounded. Okay, squaring numbers changes things. That one's probably still gonna end up being okay, but still, it's a better safe than sorry. If you go ahead and build in that muscle memory now, you're A-okay. Okay, does that kind of help out a little bit? Okay. How do we feel about standard deviation? So what does that mean? You just got a number. 15.2. What in the world does that even mean right now to you? Well, let's look. Okay. Here's the so what. I always like to, so what? Whenever I'm teaching, like on Sundays in my Bible class, I'll teach people stuff and then, they're hearing me talk and finally I go, so what? Well, let's find out. What's the implication for you? Why the so what? Here's the so what. Here's a little thing. Let's pretend, this is my own little thing here. Let's pretend you're gonna go off and you're gonna go buy some cryptocurrency today. These are not real prices. Do not go buy cryptocurrency today. I'm not a financial advisor and therefore I'm not gonna advise you on buying cryptocurrency. There's my indemnity clause. That way, because this goes online, and so somebody goes, that professor down at NMJC said to go buy crypto today. No, I did not. Did not go say buy crypto. But let's say you were gonna. And this works for stocks, anything. Let's say if I knew that Litecoin had a mean price of say $30. Okay, so here I am. I'm at $30, okay? This is what that standard deviation is saying. It's saying, hey, your standard deviation to this guy is 502. That means it can vary plus or minus $5.02 from that mean. Whereas, let's say Dogecoin, I made this before it became a government office. Let's say its average price was $100. Those things cost different, right? But, okay, so I got a mean here of 100. It's saying this swing for this guy is going to be plus or minus 1786. So if I was looking at buying something, I might say, hey, which one looks a little bit more volatile? Just kind of depends, right? Like right now, you might look at it and go, well, I don't know. I think I probably, if you're looking for a safe bet, I might go with Litecoin. Because at worst case scenario, I spent 30 bucks, I either lost 5 or I gained 5, right? But overall, I'm not going to be doing too bad. If I was just going to go on like, I'm going to try to jump in and jump out like everybody those get rich quick schemes, right? Whereas Litecoin is $100 and it's 1786. Okay. It's got more of a swing, it would seem, doesn't it? Okay. There's a problem in this theory, and I'm going to show you in the next slide. Now, unfortunately, your calculator does not do this for you. Okay, there's a thing we call the coefficient of variation. And it's usually what it does is it measures two different things. Can we all agree that while these are both measuring a cryptocurrency, they're not the same? One is $100 and it's got a standard deviation of 17. One is only $30, but it's got a standard deviation of 5. That 5 may be more of a swing than you think it is for the amount of money that you're paying for it. Okay, there may be a lot more volatility. So what we do, and I'm just going to show you the whole thing. Here you have two little graphs, okay, that we've got a nice little curve we can kind of see. Notice that you can kind of trace that out more or less, but this is what we're looking at here. Coefficient of variation. Notice when you read this, it's actually talking about two separate things. One of them is talking about farmland. The other one's talking about what? Amounts of rainfall. They're not the same. Okay. And so I'm trying to decide which one has more variability. Which one's further away from the mean, okay? Comparatively with its standard deviation. Well, you look for this. The larger the percent, the further, the more, okay, kind of varied it's going to be. Is that going to help you see it a little bit better? That's like one question on your homework. I don't want you to think about it too much. Where this comes to play in the real world is literally when you start seeing people comparing two different things and they try to compare them like they're the same thing. Like I just tried to trick you into thinking, hey, if you spend $100 and it only has a swing of 17, that's probably better than spending the, 30 and get the swing of 5. I don't know. I don't know which is better because I don't know the coefficient of variation. If I wanted something that was safe, I'm going to look for the thing that has the coefficient of variation that's smaller in the percentage. Okay? Because a large one means, man, things are getting farther and farther away. That dispersion is getting further and further away comparative to its mean. Because that's what we're studying. What's happening away from the mean? What's happened after I poured the dye into the water? How far does it spread? Okay? If I pour dye into water, we can agree it's going to spread pretty far, right? But I've poured dye into like KY, it's not going to go very far, very fast, because it's thicker. Okay, take it in wax, it's going to go even less. Kind of makes sense how things kind of spread. Okay, so let's look here, and here comes your empirical rule. One of the few things you're going to have to memorize. What's that symbol?
Mu.
Mu. Mu stands for population mean. This right here, they're going to call this a bell curve. Okay, it is. You're going to see this a lot. Happens in nature all the time. It's also called a normal curve. We'll get into that. Okay, but I kind of want you to know bell curve, normal curve. Notice its properties. Is it skewed? No. Okay. Is it symmetrical? Yes. The only difference between a real bell curve and my bell curve is a little bit off. You wouldn't even know I had told you. Do you remember in college algebra, you learned the word asymptotic? Asymptotes. What is an asymptote?
Those lines that never meant to be.
Exactly. They never touch, right? This line right here, is your X line. Okay, this right here, this line here will never touch the X. It's asymptotic. They shoot out to infinity on either end. They'll never, ever, ever stop, okay? But the total area equals 1. I know that sounds counterintuitive, take calculus. Okay? A nice little paradox for you is that if I had an angel horn, you know what an angel horn, those things angels blow into, I could fill it up, even if it was infinitely long. But I could never paint the outside of it. I'd never have a paint. It'd be infinite. Kind of a paradox, isn't it? Well, same thing. Good on that so far? Okay, what are you gonna see? Why does this matter? Because when you take standard deviations, this is why you start liking them. Variance kind of hard to explain. Standard deviation though, watch this. You have a mean. Remember, it's always based around the mean. Okay? When I go plus or minus 1 standard deviation in any direction from the mean, 68% of my data is going to fit within 1 standard deviation. Okay? Can you see that? Look. Here's my mean. There's my mean plus 1 times that standard deviation. Over here, it'd be mean minus 1 times that standard deviation. 68% of my data fits right there. This was a sobering moment for me when I took a statistics class, because I lived my life like you lived yours and thought I was unique. And then I realized, oh, I'm not. Because even when I'm trying to be unique, I'm just fitting into another bell curve somewhere else. And so I'm not unique. I'm just like this over here. I have unique thoughts. I have unique experiences, okay, that are unique to me and how I react to them. But I can gather a lot of information over a lot of people over this right here, okay? It's actually kind of scary. Well, guess what? 2 standard deviations, 95%. Anything within 2 standard deviations, okay, we would consider that normal. You want to know how to catch you cheating? Standard deviations. That's it. I have to do nothing. All I do is I run a little program and it says she did her homework. The mean of people doing their homework, the mean time is this. When I can calculate mean and I have the data of a population, can I find a standard deviation? Yeah, so let's say the mean time is 30 minutes. My standard deviation is 5 minutes. So I would suspect that between 25 and 35 minutes, 68% of my students, roughly, should fit within this time. And then I go looking, oh, it's correct. Then I go to 2 standard deviations. Okay, that means 95% of y'all should fit within these times. But then, after this, what's going to happen? Beyond 2, in either direction, I'm just going to say it, guys, it's weird. It doesn't happen very often. So, here I am. Average time, 30 minutes for test, right? 5 minute standard deviation. 25, 35, sounds normal, right? 20 and 40, I'm still good with that. Anything beyond that though? So if I have a student over here doing their homework in less than 20 minutes, guess what's happening? You've piqued my interest. How are you finishing your homework? You're now better than 95% of the class. I go look at it, and then what I do is I send emails. I go, then I put you into my office and go, prove it. Okay? But then I also look on the other end, because remember, I'm going backwards. What if a student's taking longer? Hey, that's me, you need to reach out and go, hey, is there something going on? Do I need to help you out? You know what it usually is though? A student leaving their browser, like just open and walking away. I know what that is because Hawks will tell me, they go, they didn't move their mouse for an hour. Okay, I'm like, okay, cool. But if I sit there and they're trying, that's me. I can have these ways of these checks and balances, right? And it's eerily accurate, okay? And it becomes really accurate after midterm, okay? There's a really direct correlation between time spent in Hawks and grades. Okay, I've proven that over semester by semester. So right now, what you have to memorize is this for sure. One standard deviation, 68, right? What would be your mu? What would be that? What would be that? If I had to say, what is this right here? All that right there. Wouldn't that just be 50% at mu? 50%, right? Two standard deviations, 95%. Three standard deviations, 99.7. We usually calculate the three standard deviations. You can have more. You can have 17 standard deviations. The chance of that happening, nothing is zero in this class. You will never have zero probability, ever. Okay. And this is what this really is. This is saying, notice how I kind of use y'all an example, right? I said, hey, when I go out one standard deviation, I'm expecting to see 68% of you in this area, right? Is it perfect? No, it's not. You know when it gets perfect? The more I test. Irony. All I need is 10 of you, and it's pretty dead on. It's about 60%. 20 of you, I'm hitting around 67%. 100 of you, I'm hitting 68% every time. 68% of the data always falls in. It's a very weird natural occurrence that happens. Okay. So it actually helps. The more students I have, the more accurate my data is. Hence why things are kind of fuzzy in statistics. You take a small sample size, it's not going to be kind of correct, right? But the more you learn, the more things get more accurate and better. It's kind of a underpinning of this class. Should be an underpinning for life. The more you know, or the more information you gather, the more you should know. Okay. So look at this. You can also do that. That is going to be something you're going to need to fill out on your empirical rule quiz. Which in actuality, if you think about it, if you know you're 90, if you know you're 68, you know you're 95, you know you're 99.7, well, think about it. All that is at that point is division, right? You're kind of dividing things out. This line right here, this 0.15, that goes on to infinity. This is the area from here to infinity. And from here, positive infinity for that area there. It never touches. We have one type of distribution. This is called a normal distribution. We have one type of distribution that touches and starts at zero, but not this one. You will always be working with this one right here most of the time. And like I said, beyond two standard deviations, it's weird. It doesn't happen a lot, depending upon the circumstance. Now let's think about it. If I went to go hang out with the volleyball team and we took sizes, let's do basketball teams because those are some beanstalks this year. Wouldn't I, if we took the mean of sizes, okay, the mean height, and then all of a sudden we took the standard deviation of that data, right? Where do you think I would probably fit? Would I fit within one standard deviation? How about within two? Would I probably be beyond two standard deviations away from the size of that? Yeah, I'm an outlier. I'm a big outlier. The chances of me being on there is very weird. So, sorry. So don't think of weird as improbable. It could happen like in that scenario. But now take one of our beanstalk players and put him next to what's a big time, I don't know, like those Chicago Bulls. I know that one. Take him and put him with Chicago Bull players. Is he going to be kind of normal? Notice he will be probably within one standard deviation of what we're talking about. So you kind of see how it depends on context, you know, of where something sits. Like me against basketball players, I'm going to be an outlier. You know, me against you guys, guess what? I'm pretty normal. You know, so are you. You hear this all the time. People say, well, my weight's, you know, it's not normal, or I'm this, or My intelligence is this, if you're within 2 standard deviations of something, you are 95% of the population. You're not as weird as what you think you are. Okay? So far, so good? And there you go. Notice, knowing that, you can work out some very easy math. This will become way more important for you to understand, but this is basically saying, hey, 84%, when I add it all up, 84% of my data should fit from here back, right? It's area under the curve. Congratulations, you don't have to take calculus to learn how to do that. You're just giving it to you. We've kind of just solidified the. One little formula you're going to have to use, unfortunately, and it is going to be on your midterm for one question, okay? There is a thing called Chebyshev's theorem. Now, what we do is we use this one right here. We use this all the time. 1 standard deviation. Remember how, look how I'm saying it. 1 standard deviation, 2 standard deviation. I'm not doing 1, okay? It's 1 away, plus or minus. 2 away, plus or minus, okay? 68, 95, 99.7. And then if you kept going, 100%, obviously, okay? Chebyshev's theorem says this, though. Hey, I'm going to give you a formula because he said, what if there's some weird numbers? Let me give you a little. It's always going to give you some nice whole numbers, okay? If you took an upper level stat class, they get weird numbers. You're not going to worry about that. We're going to get some pretty numbers. Okay, you don't got to write this down because they're not even giving you a formula right now. Okay, let me just show you what the formula is. You do need to know the formula. The formula is this. K, note our K's, okay, is equal to some piece of data minus the mean divided by, what is that symbol?
Sigma.
Very good. Sigma is
Duration.
Greek, yes, but it is,
Variance.
oh,
Standard
standard deviation. You're going to get it. Remember, powers of 2 are variance. Okay? So let's do a simple question real quick, kind of a homework help. Well, you're going to do it. I'll help you though. Suppose that the prices of milk at various stores in one town have a mean, okay, of 375 with a standard deviation of 0.15. Using Chebyshev's theorem, what is the minimum percentage of stores that sell a gallon of milk for between 3.45 and 4.05? Round your answer to 1 decimal place. Okay, well, let's take a look here. Knowing our formula, I'll write it down again for you. We've got K is equal to X minus mu all over sigma, which is
Standard deviation.
very good population standard deviation. Let me do this so that way you remember it on a midterm. Well, we have a couple of X's, but let's worry about our mu. We have mu here. Do we have a mean?
Yes.
Yes, we have a mean of 375. We also have a standard deviation of 0.15. Well, we have a formula now too. And unfortunately, your calculator does not do this theorem for you. You have to do this yourself. Okay? So notice they give me 2 X values here. I've got 345 and I've got $4.05. Here's what it is. Now, we're going to do the math, and then hopefully this helps you understand things a lot better. Okay? You're searching for milk. Remember, that is our goal right now. Okay, dads, future dads, you're searching for milk because you want your significant other happy, and you've only got this much money. Okay, so how many grocery stores out there in your town are going to have these milk prices that are between $3.45 and $4.05? Let's find out. So we have to do these equations twice. We've got an X value of 3.45 minus 4.05, and we're going to divide that by 0.15. But I also have one that has what? 4.05 minus, sorry, That's it right there. That's 3.75, because that's my mean. And then 0.15. When someone gets one of them, tell me what you get. Super simple math. You louder?
2 and -2.
Very good. We have -2 here and 2. Well, what does Chebyshev's theorem say? If you have a 2. There you go. 75%. So it's saying, bless you. It's saying 75% is your answer. I'm saying, great, that gets you a green bar. But I want to know conceptually, what is that saying? What do you think? What is that 75% saying to you right now?
So the stores that sell it,
Very good. Say it a little louder. That was perfect.
the minimum percent of stores that sell it.
Yeah. If you know you have this much money, okay, and you can be almost assured, is it perfect? No, it's not perfect, right? But you can say, okay, we're gonna be okay, honey. Milk at around 75% of the stores, okay, it's gonna have these milk prices. There we go. So no matter where I go, I'm probably gonna be okay. Now, is there a possibility out there that you could find milk for less than what you want? Yeah, that'd be awesome, right? There's also a possibility you could be hired, okay? But this is what that theorem says. But that's also what your standard deviation is saying. If I switch this out for standard deviation, you could say, well, within one standard deviation, the thought of me finding milk for between this price and this price is 68%. This price and this price, 95%. Beyond that, probably gone a little weird, but that kind of makes sense, more sense now? Okay. Here's a good one about IQ scores, and this one is pretty exacting. They haven't updated IQ scores or the totality of it in a while. Here's where I want you to start learning to do something. It's going to help you not just do good and understand things. It's going to help you pass this class. Okay, you're going to need to start learning to be an artist, even if it's a crappy one. I don't care. Start drawing yourself little bitty bell curves. Then you kind of start understanding things, okay? So look what this says. Suppose that IQ scores have a bell-shaped distribution. That's what we just learned about, right? With a mean of 105. Well, I know mean is right here. And a standard deviation of 15. Using the empirical rule, what you just learned, what percentage of IQ scores are between 90 and 120? Notice it's saying this right here, that standard deviation is always plus or minus 15 from 105. So notice if I do 105 plus 15, what do I get?
2020.
Exactly. But then I do 105 minus 15, what do I get?
90.
Oh, well, look here. So if I start here at the mean and I come one standard deviation, I can color all this in right here. What is the number that would go inside there?
68%.
There you go. So 68% of the population, and I'm guarantee you, it's pretty exact, have an IQ between 90 and 120. 130 gets you into Mensa. Everybody know what that is? No, I think it's 140 now. Mensa is the they basically call it the Genius Club. Okay, you take an IQ test, you get into it, it's because you have an IQ of over 140. Okay, so, but notice that would be kind of an outlier, wouldn't it? Because guess what? If I add on 15, what's going to happen? Yeah, plus 15 is going to give me 135. Well, notice that's one more standard deviation. What's everything beyond 135? Really weird, isn't it? It's kind of different. So anything above 135, if somebody has over 135 IQ, that's like, oh, you're not okay, I say this, you're not normal in the sense of like, you're not like the 95% of the rest of us. So that one person you know of who brags about stuff, go look up stuff about them. When someone says, man, I have 121 IQ. What should that tell you right now? They're normal. They're within 2 standard deviation, be like, you're not special, you're within 95%, you're like the rest of us. Okay? Weights. Look up weights. What's your weight compared? Hey, it's probably within 1 or 2 standard deviations. Okay? Very quickly, we'll do this one, we'll finish off. I think there's one more homework problem that's gonna be on your notes, so don't worry. Looks to me like there's something up here that I only have to use my calculator the hard way one time, right? What's that?
Relation standard or record.
Looks to me like, I mean, if I'm gonna be honest, my range is the only thing I'm actually gonna use my calculator the hard way for. Because don't I have a button to do the rest of it? Yeah, everything else. Okay, so here I'm gonna do 15 minus 6. That's gonna give me a 9. The rest of this, I'm putting into a list function. Put it in your list, tell me what you get. Round your standard deviation to 1 percentage point. We actually do have one more, and I think I have time to get to it, because you do kind of need help on this one. It's kind of it's a question. What'd you get for variance? But let's see, what are you gonna give me first? You wanna give me standard deviation?
Standard deviation, 27,
Round it to the nearest 10.
20, or 29.
Very good, 2.9. So how would you get your variance? Square 2.9. Now, would you square the 2.9? Square the 2.8. I think even on mine, I think I did it wrong that way.
8.2.
Was it
8.2.
8.2?
Yeah.
Trusting y'all on that, I didn't do it on mine.
8.2.
It's 8.2. I think on your notes, I think it was 8.4 because I did a mathematical error. You know what I did? I squared from the rounded one. Never square from your rounded. Okay. Last one, help you out here. This is a great one to use to do your drawing because it's going to help you out. Notice here, suppose that the grade point averages for undergraduate students at one university have a bell-shaped distribution. That tells me I'm going to have this, correct? With a mean of 2.54 and a standard deviation of 0.44. Using the empirical rule again, what percentage of the students have a grade point averages that are less than 2.1? So notice you got to come in here, you got your mean, and you're gonna plus or minus 0.44. I think we can all agree I don't need to worry about the plus, right? So when I do the minus, I do 2.54 minus 0.44. Notice what I get. Right here is 2.1, and I'm looking for what? All of that. So how would I figure that out? Let me give you some hints, okay? I know for a fact, right here is 50%, right? I also know that in all this is 34 and 34. So can I do 50 minus 34 and get 16%? Right? Or can I also do this? I know that I've told you how to calculate the 3 standard deviations. I know here is going to be 0.15, 2.35, and then 13.5. Do you see why it's important to memorize all those little things? Now you can always add all those up, and you'd also, once again, you would get 16% again. Okay, but notice by drawing my picture, doing the little subdivisions, it really helped out a lot. Okay, it's going to get harder if you don't start learning to draw these little sketches. Okay, you need to see what you're seeing, and I promise you, it's going to make the calculator work mind-numbingly easy because you can see and go, oh, this is what they're saying. They want from here to here or from here back. Okay, I promise you. Good. Day one, standard deviation, but now you know what it means when we say standard deviation. Okay? We're gonna keep using it. It's gonna become very important in chapter 4. Okay? So everything kind of melts together, so we're gonna be okay. Good? All right, I'll see you guys later. If you have any questions, please email me and I will see y'all next week. All lectures will be downloaded completely by tomorrow at the latest.